All right, today we talked about laminar pipe flow and kind of carried it all the way through from first principles to aggregated integrated energy loss along a stretch of laminar pipe flow. First of all, let me just note that for the pipe Reynolds number defined by RED, which is the average velocity in the cross section times d over nu, less than about 2,000 flow is laminar. And so the results I'm going to summarize here are all subject to the limitation that the Reynolds number is less than about 2,000. Sometimes it can hold up to maybe 2,500 or something, but 2,000 is a good rule of thumb. Okay, first thing is to talk about the velocity distribution in the cross section of a pipe. And so if this is a pipe of radius r equals 0 along the center line, the question is, what is the velocity in the cross section as a function of r? We went through the solution of this starting from the Navier-Stokes equations, and I'll just give you the key result that u of r is given by minus 1 over 4 mu dp dx, where x is the flow direction that's drawn here, times capital R squared minus little r squared. And what this shows is that it's, first of all, parabolic. The peak velocity is at the center line, at little r equal to 0, and it is in the down gradient direction of the pressure. So when the pressure gradient is negative, velocity is positive. So for the way I've sketched this on the left here, with x in the left to right positive direction, that means the pressure gradient has to be directed with higher pressure on the left, and so you'd have something like this for P versus X. So flow is going from high pressure to low. Then we can integrate this and define the averaged velocity and so on. The key step that we did near the end of lecture was to think about the energy equation and the energy loss. And we'll call that head loss, say, h sub f, the head loss due to friction. And what we do is we integrate the velocity between 2 points over a distance L, capital L. The head loss is given by 32 times the absolute viscosity mu times the length scale, which is capital L, times the mean velocity divided by gamma d squared. Now, what we're going to talk about next time is generalizing this into something known as the Darcy-Weisbach equation, which formalizes the head loss as F times that distance L over the pipe diameter mean velocity squared on 2g. And so this combination implies that F for laminar flow is 1 over 64 over the pipe Reynolds number. And all three of these expressions, or I should say the expression in blue and the pair of expressions that I've circled in red, are equivalent. For the case of laminar flow, the head loss is given by this expression in blue, or can be dimensionally given by the Darcy-Weisbach equation inside the red circle, as long as we have a friction factor F given by 64 over the Reynolds number.